Hello,
Oh,
hello, Ross. How you doing?
I'm fine, thanks. How are you?
Yeah, good. Thank you very much. Thank you very much for agreeing to talk to me. Really appreciate it. Thanks for finding the time as well.
Sure.
And it looks like you've got an excellent internet connection as well, which is uh,
Uh,
which is great.
yes,
Because
despite being in remote West Wales, yes.
I guess maybe the good place to start is it? I don't know if it's possible to explain DNA computing, even if that's the right terminology that I'm using.
Okay, so all computers, electronic computers we use, our mobile phones, etc., are uh, in computer science. There's we consider all these computers to be uh, instantiations of this abstract idea of a Turing machine. So a Turing machine is a mathematical concept, but it's electronic computers are basically instantiations of this abstract idea.
Okay.
And every form of computer we've been able to think of is either equivalent to a Turing machine or less powerful than a Turing machine.
And what
Okay.
is a Turing machine?
Uh, that's basically it was an idea that Alan Turing had back in 1935. Uh, After a long, he was a very keen runner, and after a long run, he had a rest in near Cambridge, and suddenly this idea came to him about this abstract machine. And it's a very simple type of machine. So what you have is a tape, like a paper tape, and or a roll of toilet paper or something which has squares on it. Yes, and on these squares there are some symbols. And the machine, what it can do is look at a square of the tape, recognize the symbols there, uh, look up inside itself a little lookup table where it says, if I see this particular symbol and I'm in state, uh, say X, then change to state Y and write a particular symbol on that square and move left or right. Okay, so that's all it can do. It can look at a square, decide to change its internal state uh, in a fixed way. There's only a limited number of internal states, and move left or right on the tape. And the tape is in some sense unbounded. Okay,
Okay.
and Alan Turing showed that using this type of device, you could compute lots of different things. And it's turned out that everything we think we can compute, a machine like this can do. Okay, this is an abstracted idea.
Yeah.
And he also had this idea of what's called a universal Turing machine. That's a Turing machine which can basically emulate any other Turing machine by looking up a program on it. By looking at the different states on the tape, it can program itself to be like any other type of Turing machine.
Okay.
And that's what our electronic computers are like that. You program to do different things. You don't need a separate computer to do arithmetic or to play games or something. You can program to do anything. Yeah.
Yeah.
There's this abstract idea of what's called a universal Turing machine. And electronic computers are basically just an electronic instantiation of that idea. And coming to DNA computing, so because we know that there's this general idea of a universal Turing machine, we can make a universal Turing machine out of bits of DNA, just like we can make it out of electronic components. Is that clear, or is it? It's
Uh,
quite an abstract idea. It's
yeah.
not,
No. Completely.
not the idea for.
Does it? How does? Is it because he Alan Turing invented the bomb, didn't he? Is that? Would that be described as a Turing machine or not?
Yes, I think it's a Turing machine, but not a universal one.
It's not a universal one because They couldn't.
It was specially designed to crack Enigma codes
Yeah.
which the Germans used in the Second World War.
So the universal Turing machine idea came after the bomb. Then
No, it came before.
it
Came
came
1930.
before.
Yeah.
So that was just theoretical, but
Yes.
he realised the Turing machine, but never realised the universal Turing machine.
Yes, he had that in his paper as well. Yes, and he also proved that there are certain things which universal Turing machine cannot compute. Specifically, whether arbitrary computer program will stop or not, or continue forever. Okay, so there are certain things which are non-computable.
Okay, that's interesting. So then, can you explain your research then into so I'll get this right, non-deterministic universal Turing machine? Then,
yes.
obviously
Okay.
you're going to have to explain very slowly, as you are to me already.
Yeah, well, these are quite hard ideas. I've worked in other areas of science and try to explain to journalists and things about it. And this is particularly hard because it's you have this abstract ideas of Turing machines, and then you have molecular biology, and it's all a bit confusing. Okay, so my contribution was so I told you that all Turing machines, universal Turing machines, are equivalent in some sense. Yeah, so that your laptop is equivalent to a supercomputer or your mobile phone in some sense. They can all compute the same functions, but obviously some are faster than others. Yes.
Yeah.
And so there's a branch of computer science called the complexity theory, and what that's concerned with about how difficult certain problems are to solve by a computer. Okay, and how it works is if you double the size of the problem, does it take twice as long on a computer, or maybe it goes up by the square? It should be 4 times as long, or maybe as the cube, which should be 8 times as long, or something like that. Yeah.
Yeah.
Yeah. So if it's concerned with when you change the size of the problem, how long does it take the computer to solve that problem?
Yeah.
Yeah. And computer scientists divide problems into 2 types. Ones which we think are tractable for computers. These are sort of what we call polynomial problems. And ones which are not tractable. These are exponential problems. So the polynomial ones scale as a square or the cube or something like that. Yeah.
Yeah.
Whereas the exponential ones scale as an exponential number. So that's you understand what an exponential?
Yeah. So it increases over time.
Yes. So instead of so if you in a square like 2 to 4, when 2 squared it goes to 4, when 3 squared it's 9. Yeah. So
yeah. So there's an upward arc.
There's a 2 is a constant there. Yes.
Yeah.
Yes. So you understand. So that the n to the power of 2.
Yeah.
So the 2 is a constant.
Okay. Yeah.
In an exponential, it's the other way around. You would say 2 to the power of an n is the number you're other way around. You see. So if you had 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16. So that is going up much faster than a square would, or a cube, or any other constant there. Yes. So there's a fundamental difference. You often hear politicians say that something's growing exponentially, but they don't really understand what that means. But it's like living systems are like that. So if you have 2 rabbits, you have 4 rabbits, and 8 rabbits. That's growing really, really fast. Yeah. And such problems which scale like that, we consider in computer science to be not tractable. Yeah.
Okay.
They're too complicated to solve. And unfortunately, most problems in the real world are like that. They scale exponentially. In particular, there's this set of problems called the NP-complete problems. Okay, and I'll try to explain this to you.
Okay.
So The NP-complete ones are the most important practical problems in the world, actually. They're really the most important for solving real-world problems. And they have this interesting property that if you tell the computer the solution to the problem, it can check that there really is the solution in polynomial time, which means it can do that attractively. Yeah. But if it's hasn't been told the solution, it doesn't know any way of finding that solution apart from an exponential time. Okay, so they have this asymmetric feature that if you tell it the solution to the problem, then the computer can check that really is the solution in a tractable time. But if it doesn't know the solution, it can't find that in tractable time. Okay.
Okay.
And the biggest problem in mathematics and computer science is whether these things are really different or not, whether polynomial time is really different from this NP-complete time.
Okay.
Yes. It would seem intuitively that it's harder to find solutions to problems than to check solutions to problems. But no one's ever proved this.
Okay.
And it sounds arcane and sort of not particularly important, but it's our whole system of life depends on this asymmetry at the moment. So the reason that mathematics is hard, that there's certain problems in mathematics we can't solve it because of this sort of state of situation. So that if I give you the proof of a particular mathematical question, it's quite easy to check the proof.
Yeah.
But no one knows how to find proofs of certain problems.
Okay.
And internet banking, for instance, depends on this asymmetry. So it's the security of cryptography depends on the asymmetry of this problem. So there's it's really important. So it could happen tomorrow that some mathematician proves that P actually equals NP, and then there would be no safety on the internet at all. There'd be no security. The banks.
Okay. Yeah.
There's money. It's basically data structures and computers and banks. And if there was no security there, anyone could hack into them. Then there'd be no more money. You know, it'd have to be sort of go back to the old days of where money really was bits of gold or something.
Twigs, wasn't it? Actual stakes.
Well, I think they started off as barley. It was original food.
Oh, was it?
Money. Yeah. Which is good because you can eat it if you get desperate. Unlike your credit card, it's not going to help.
Yeah.
Okay, so there's this huge problem about the complexity, how difficult certain computational tasks are to do. Yeah. And this important set, these NP-complete ones, are how it was originally defined as the problems which a non-deterministic universal Turing machine can solve in P time, that's intractable time. Okay.
Yeah.
So there's a long way back to this, but that's the point, is that you could actually build a non-deterministic universal Turing machines. If I really had one in my hand, I could solve any mathematical problem. I could break into GCHQ, no problem. I could do all these different things.
Yeah.
So it's really nice to have a non-deterministic universal Turing machine. Okay. So what we did was we sort of built one, but there's a catch. Yes. It really does get exponentially faster and could do all these things. But unfortunately, it takes up more and more space as it solves a problem. So you understand?
Okay.
You understand what I'm saying? So it gets faster and faster and really could do all these wonderful things. But unfortunately, it takes up space as well. So eventually, there's not enough space in the lab or in the planet or in the universe to solve a certain problem.
And this is if it's running with DNA.
Yes.
So it has to replicate DNA because it can calculate, because it can do multiple calculations at the same time.
Okay, I'm going to try and repeat that. So yes, so it's like when a non-deterministic universal Turing machine tries to solve a problem, every time it comes to a choice point in the computation, it replicates itself, and one computer goes down one part of the maze and another one goes down the other part of the maze. So it's like, if you imagine trying to find the solution to a maze, every time there's a choice point, instead of having to decide whether to go left or right, you split yourself in two, and one half of you goes left and one half of you goes right. Or one copy of you goes left and one copy of you goes right.
Okay, and this is all done through DNA.
Yeah, because the wonderful thing about DNA is that it can copy itself. That's why we get babies, and yeah, exactly. So it's the duplication of itself is the wonderful feature. It can not only store information and compute things, but also can copy itself.
Okay. I guess that's quite a crucial point, really. I mean, that's the main advantage to DNA for computing, rather than anything and non-biological.
Well, it's
materials.
one advantage. It's also so it's our electronic computers. You have to go to the shops to buy a new one. They can't copy themselves. The other advantage is that DNA is very, very small, so that it's much smaller than the components in an electronic computer. And that's good because I said every time it copies itself, it takes up more space. So eventually, you run out of space. But if you start really small, that gives you a big advantage. So there's a thing called Avogadro's number, if you may remember from school. It is the number of molecules in a mole. And that's an enormously large number. It's roughly 6 times 10 to the 23. It's unimaginably large number. It's trying to think how to. So there's, I don't know what, less than 10 billion people on the planet. So that's 10 to the 10.
Yeah.
So it's 10 to the 20 is 10 billion times 10 billion.
Yeah. Okay, yeah.
and if you multiply that by 3, by 1,000.
Yeah.
It's 1,000 times 10 billion times 10 billion times 6,
okay.
That's so a mole of water. That's like a pint of water or something, much less, actually less than that. So there are so many molecules. Molecules are incredibly tiny.
Okay, that's incredible. Yeah, I mean,
it is incredible that how small our component parts of living systems are.
Yeah, and also with DNA, because obviously I've been looking into DNA data storage. It can store information as well. That's it.
Yeah. Mm-hmm. But storage is a bit boring compared to replication, I think. It's what's really interesting about DNA is, as you say, it can replicate itself, which is a much more interesting thing than just being able to store data for the long term.
So why for you is replication more interesting than storage?
Well, it's computation is more interesting than storage.
Okay.
It's like a computer is more interested in than a hard drive. It's a hard drive on its own doesn't do very much. If you add a computer, then you can do an infinite number of things.
What would a DNA computer look like then?
So it looked like basically plumbing. It's you have liquids flowing around. All the actual action is happening at the molecular scale, so you won't see it. It's just like you don't see how a computer works. It's just a piece of. Even if you pull it apart, you don't actually see the electrons moving around. You just see bits of hardware, and the bits of hardware in a DNA computer would be the sort of plumbing of the system, so called microfluidics.
And so, but rather than a normal computer, it would be moving. It would have to be fluid to operate then.
Yes, but all the action's happening at the molecular level inside the fluid. So it's bits of DNA are being modified to others. So DNA has. So how it works and how genetics works is that DNA is a digital code. So there's 4 letters: A, C, G, and T. Yes, and they encode information about how to make living organisms. Yes, so it's like a symbolic code, and these are symbols, and the DNA computer would look at these symbols and change them to other symbols, just like on the tape of a.
I know that you in sort of one of the articles I read, you said that DNA computing will be better than quantum computing. In what way, will it sort of like outperform quantum computing?
Okay.
And maybe in that as well, if you could give me a little explanation of quantum computing as well. So.
Okay, well, first, I told you that there's this set of problems, these NP-complete ones, which are
Yeah.
the most important practical problems in the world. Most people think that there's no way to solve these problems apart from a brute force search approach like the DNA computing does. Yeah, so it's basically it just tries everything. It's to search a maze, you search down all the paths at the same time. There's no shortcut to solving maze problems. That's what most computer scientists and physicists believe. Uh, Quantum computers, when they search a maze, they also, in some sense, can search down the different paths at the same time. But that only works if the maze has certain symmetries. It doesn't work for arbitrary mazes. So if the maze has certain nice symmetrical patterns in it, then the quantum computer can search down all the paths at the same time. But if that maze doesn't have these patterns, this particular structure, then it probably won't be able to search down any faster than a normal computer, really.
And how does quantum computing work exactly?
Okay.
I know it's not your field, so
Well, this is even harder to explain. So it's so the world. So when Alan Turing invented the Turing machine, he thought he understood what paper and tapes were and things like this. But it turns out that the physical world isn't what we call classical. It's quantum mechanical, and that means that it has certain sort of strange properties, which we understand very well the mathematics of what's going on, but we don't really understand what we call the ontology, what it means, what's really there physically. Okay, so in classical physics, the world is what's called deterministic. So if you know the starting conditions, then you can predict what's going to happen in the future with perfect accuracy. Yes.
Yes.
So we have a set of what are called differential equations, which you have a starting conditions. Then to predict what's going to happen, you just run these differential equations, and they predict what's going to happen at the end. They tell you what's going to happen at the end. Yeah.
Yeah.
Quantum mechanics is the same, but it involves differential equations. The main difference there is that it's involves complex numbers, but that's not that different from classical physics. The real difference comes when you want to say what happens at the end. So there's this very strange rule that says that what you do is you essentially take the complex number you have and you square its modulus and interpret the number as a probability. Okay, so you don't find out, it won't predict exactly what happens, but it just gives you a probability about what will happen. Okay, That's the fundamental difference. And for the best part of 100 years, we've been trying to figure out why that is the case. The person I think is probably the most fundamental person for the foundation of quantum computing is a person called David Deutsch. I don't know if you come across him.
No, I haven't.
Anyway, his interpretation of what's going on is that the universe, well, his interpretation of quantum mechanics, of the many worlds interpretation of quantum mechanics. Yes. So instead of, he says that what happens when, say, an electron has to decide between going between one hole or another hole. Yeah, so you're firing electrons one at a time, and they go through one hole or the other hole. But in quantum mechanics, you don't know which one it went through. Yeah. And his interpretation of what happens is that the universe splits every time there's a sort of choice point for quantum mechanics. so that in one universe, the electron goes through one hole, and in another universe, it goes through another hole. So instead of there being a probability of something happening, what that probability is of you ending up in one or the other of these universes.
Is that the two-slit experiment?
Yes, but so that it's very clear what happens physically, but what's unclear is the ontological interpretation of what's going on. What really happens in the physical world? Is there some sort of coin tossing in one world, or is that the universe splitting into separate worlds? And he is a great believer in the splitting of the worlds. And he thought perhaps we can use that for computation. And that's how he came up with the idea of quantum computing. You don't need to believe in that for the computer to work, but it's how he was inspired to discovering this idea. So he believes that when a quantum computer works, it's using these other universes to do the computation. And you can get the answer back in every universe, only if the problem has some sort of symmetry.
So back to DNA computing. I mean, I think I'm going to sort of ask two questions as one. Like, um, uh, what applications do you predict it having for the future? And also, is there? I mean, in terms of it using DNA, is there potential to use our own substrates as computers?
Okay, so potentially, for a DNA computer, you could solve more difficult tasks than even the biggest electronic computer could at the present. Yeah. And crucially, using a fraction of the energy. So computing is taking more and more of a share of the planet's energy resources, and that's non-sustainable. So the next generation of supercomputers, exascale ones, they're estimated that one computer would use the same amount of energy or same amount of power as, say, 50,000 American homes, just for one computer, which is it's crazy. It's not sustainable. Given global warming and things like this. Whereas DNA computing could potentially do the same amount of computing for a tiny fraction of the amount of power. So that's probably the main advantage of the system. And to your second question, yeah, so the original motivation for this research was as in a field called synthetic biology, where we want to sort of basically re-engineer biological systems to do useful things. And the way that biological systems are currently controlled is, for human engineers, very ugly. It's because they evolved over literally billions of years. They don't do things in a sensible way, an easily changeable way for engineers. It's because they evolved. If you imagine the advantage, so the description that biologists often give is that if you imagine you had to evolve an airplane while keeping it in the air, from the Wright brothers' first plane into a modern plane, could you actually keep it flying and modify it at the same time? And of course, you have quite a big constraint on you if you have to keep flying at the same time. There's no radical redesign to the system. But so my idea was that we would want to really program and control biological systems more easily. You'd want to put a Turing machine into the cell and control it using a Turing machine. In fact, a universal Turing machine. Because that's like a little computer. You just put a computer into the cell and program it to do as we want. And that would be much easier to change systems to have desirable properties, make new drugs, antibiotics, and things like that.
What other potential does that have? Do you sort of foresee that having? I mean, that's like a radical change in sort of in terms of also I think obviously I wanted to sort of talk to you about AI as well. I mean, what applications does that have for AI? As soon as sort of computational technologies start to morph into sort of our own biology in a way.
Well, I'm not sure we'd want to necessarily re-engineer our own biology directly using such a system. Not straight away, anyway. That's very far off in the future. Because though you could imagine, well, people already are refactoring and reorganizing biological systems, simple biological systems, like bacteria and yeast and things like that. As an engineer, when you look at how human cells work, it's a disaster in many ways. It's not well designed, and potentially you could make it much better designed and much more robust to errors and things like that. So you have about 3 billion bases in a human genetic in your chromosomes, about 3 billion bases. Yes. And if I change just one of them, I could potentially kill you, which is very, not robust. Where in other places, I could change millions of them and it wouldn't make any difference to you at all. So it's when we design engineering systems, we want to make it more robust to change, so that if you damage certain places, it's not going to start falling apart, which happens to humans all the time. One base change in the wrong place can really kill you. Certainly can kill a baby, a fetus, and things like this. And a few base changes could give you cancer very easily. So you could potentially make these things much more robust by re-engineering them.
And what about in terms of artificial intelligence? Because I know you've done some work with the robot scientist that you developed.
Yes. So I'm interested in having AI systems help us to do scientific research, and to autonomously do scientific research. So the computer robotic system would have background knowledge about an area of science. It can then autonomously develop novel hypotheses about that area of science. Then it could autonomously develop experiments to discriminate between these hypotheses. And then it controls laboratory robotics to actually execute the experiments, which are efficient experiments in terms of time and money. And then the results of the experiments are fed back to the system and changes the probabilities and the hypotheses, and the system completes the cycle. So it automatically improves itself and learns about science.
And did you develop one called Adam?
I developed one called Adam, and my latest one's one called Eve.
Okay. Yes. And what form does Eve take?
Well, you can look on the internet. It's like I don't know, it's about 5 meters by 5 meters. It's not like a humanoid type robot. It's more robot arms, more like there's robot arms, what we call liquid handling robots, automated incubators, just lots of scientific equipment all together. It's the Japanese actually have much more anthropomorphic type robots. Something different in their culture with they prefer to have robots look like humans, whereas in European manufacturers they really don't like that at all.
That's interesting.
Yeah, I think it's culturally it's very different over there because I have research contacts there. And they have far less worried about robots taking over the world as potentially dangerous things. They see them as a very positive feature.
Yeah. Well, as on that point, maybe go back to DNA computing. I realise you've got 10 minutes or so left, haven't you?
Yes.
Are there any disadvantages that you can foresee with it? I mean, obviously, if people other than yourself work on the technology, and other people with maybe sort of slightly more negative applications.
Yeah, well, there's electronic computers are probably the most successful technology we've had ever. It's incredible, successful technology. And it's very hard to compete with 50 years of development there. And the components in electronic computers work much faster. So the clock on your computer, I don't know, it's gigahertz. That's billions of times it's ticking a second. Whereas DNA computing works much more slowly. You can maybe copy 1,000 bases a second, that sort of speed. So it's a million times slower.
Okay.
But it's because you have much more parallelism. That's how it catches up. So only for problems where you have large-scale parallelism is it suitable.
And is that quantum computing's advantage? Is it speed?
It's speed for certain problems, yes. Well, DNA computing is also fast. It's just that only if it's for certain types of problem. If you need to exploit millions of or billions or tens of billions of processors, then a DNA computer's good. But if it's a simple task which there's no option for parallelism, then electronic computers are much better. And the same for quantum computers. They have no advantage unless there's a lot of parallelism in the task.
And so where are you going with your research now? What's the next step for it?
We want to build a proper working system and show that it can compete with supercomputers. And ultimately, we want to demonstrate what we call DNA supremacy, which is showing that our computer can solve a problem which the biggest computer in the world cannot.
And how far off that are you, do you think?
I don't know, 5-10 years, I think, if we have the funding.
Okay, wow. I look forward to seeing what your results are that come out of that. I mean, its potential is amazing. I mean, I've been sort of going down this just research rabbit hole of DNA, anyway, which is sort of how I got to you. So, I mean, I thought DNA data storage was like the next big thing, but this is clearly like just miles ahead of that. And I know you've got to go, but I just want to finish up quickly on. I read that you'd made some music from protein strands.
Yes.
I just wondered if you could quickly talk about that at all, because I mean, just for me, the application of things into a creative form is obviously quite interesting.
Yeah, I don't know. So I was looking at from genes, especially encoded in proteins, and it's interesting because they have there's pattern there, but not repetitive pattern. So it's subtle. Which is quite similar to music. You don't want to just repeat the same thing endlessly. That's pretty boring. And if it's random, it's also very boring. So there's something in between, which is interesting for human beings. And so, with a musician colleague in the band, the Shaman, which was back in the early 90s, they were a big band then, we developed an encoding of how to go from a DNA sequence into music. And you can download it from the internet and try it out if you want.
Okay, how do I find it?
It should be around somewhere, I think.
What's it called?
I think actually one of my students should have put some stuff down there last year. So if you look up DNA music,
DNA music,
should find my name. You should be able to find it as a Java program.
And just explain just quickly the process of.
So how it works is you have from molecular biology. How it works is you have DNA, which is then translated into protein. And so DNA, I explained to you, there's 4 bases, A, C, G, and T. And how the translation works is that your genetic looks at triplets of these bases. And for each triplet, it translates that into a single amino acid in a protein. And there's 20 types of amino acid. Okay. And we wanted to represent this information in music. So 20 too many for individual notes. So the baseline is, well, sorry, the top line is the notes from the DNA sequence. The baseline is based on the physical properties of the amino acids, whether they're large, small, hydrophobic, hydrophilic, things like that. And these pick out a base pattern based on these different properties.
Okay, and then you put that into like a music program, or like
yes. So then it produces BD, which you can then you can play around with the mapping and the instrumentation and things like this.
Well, I better let you go.
Yeah,
but thank you so much for talking to me. Obviously, like, I know it's.
I hope you can find something from all that rumbling.
Yeah, I can tell you're a very good teacher.
Maybe if you want me to repeat some quotes, we can do it, record it better or something if you decide what you want.
Okay, brilliant. Well, much appreciated, yeah.
Okay, bye.
Cool. Thank you very much. Cheers, Ross. Bye.